Hello everyone, I'm J Wildberger. In this lecture, we're going to talk about invertible matrices and the connection between solving systems of linear equations. And a great starting point is this theorem right here that connects invertibility of the matrix with solutions of a general system involving that matrix. So the theorem is if A is an n by n matrix, so note that's it's a square matrix, then the following two statements are equivalent. Statement 1, A is invertible. Statement 2, the system AX equals B has a unique solution X, necessarily in Vn, n-dimensional space, for any B in Vn. So no matter what the right-hand side is, there's going to be a solution and it's going to be unique. So let's prove this. Proof. So in this kind of setup, we have to prove two things. We have to prove that the first statement implies the second and that the second implies the first. So let's start with the first implies the second. So assume A is invertible. What does that mean? That means, i.e., that there is an n by n matrix, we'll just call it A inverse, which has the property that A times A inverse equals A inverse times A equals the n by n identity matrix. Okay, so now let's have a look at the system AX equals B. So now consider the system AX equals B, where B is a fixed vector. We're fixing this vector. It's a fixed vector in our n-dimensional space of column vectors. How do we get at a unique solution X? What we do is we do the same kind of thing that you would in sort of primary school. If you were sort of solving for the equation 3x equals 12, okay, back in primary school, the way you solve that is you multiply both sides by the inverse of 3. The idea being that 1/3 times 3 is going to be 1, and that'll isolate x. In other words, remove the coefficient of x. So we're going to do exactly the same thing here. So what we do is we multiply both sides of ax equals b by the inverse of a. Okay, so then we have a inverse times a times x equals a inverse times b. And this is the same as, by associativity, a inverse times a times x equals a inverse b. Or, because a inverse times a is the n by n identity matrix, we can replace that. The identity matrix times x is just x. So we get x equals a inverse b. So conclusion, there is indeed a unique solution. Okay, this x works. And it's unique because we have a formula for it. Okay, good. Now, the other thing we need to prove is that 2 implies 1. We're going to assume that the system AX equals B has a unique solution X in Vn for any B in Vn, and we're going to try to prove that A is then invertible. So let's assume that AX equals B has a unique solution for any vector B in our n-dimensional space. Now, what I'm going to do is I'm going to choose some interesting and important values for B, okay? Now, if E sub I is the vector which has zeros everywhere
except for a single 1 in the ith spot. I better write this. So the 1 here is in the ith position. Okay, so E sub I is that vector for I equals 1 all the way up to n. Then let's apply what we are assuming to the equation AX equals EI. So then AX equals E sub I has a unique solution. That's what we're assuming. And let's call the solution, say Y sub I, okay? Y sub I. That is, we're assuming that A times Y sub I equals E sub I. And that's valid for I equals 1, 2, all the way up to n. So we have these n vectors yi that have the property that A times any one of them gives us this ith basis vector. Now what we do is we consider putting them all together. Consider the matrix, say, Y, which is Y1 is its first column, Y2 is its second column, all the way up to Yn is the last column. This is also n by n. Then, what is A times Y going to be? So A times Y is A times Y1, Y2, up to Yn. So I need to remind you about matrix multiplication. The way we do matrix multiplication, remember, I sort of encouraged you to think about it this way, is that the result over here, okay, is going to be obtained one column at a time. So to get this first column, okay, how do we get that first column? We take the first column on the right-hand side here, and we multiply it by each of the rows of A. A has various rows, okay? So what we're really doing when we do that calculation is we're just multiplying the matrix A times this first vector Y1. So what's happening here is that this first column is just A times Y1. And this next column is A times Y2. All the way up to the last column, which is A times Yn. That's the way matrix multiplication works. But we've arranged that A times Y1 is E1, which is the vector 1, 0, 0, all the way down. And that AY2 is E2, which is 0, 1, 0. All the way down to AYN, which is the vector with just a single 1 in the last spot, since A times Yi equals EI. So this is the n by n identity matrix. Conclusion. So we have found a matrix Y such that A times Y equals the n by n identity matrix. Great. Does that mean that A is invertible? Well, not quite. Okay. Unfortunately, this does not quite prove that A is invertible. It proves that A has a right inverse, but does not prove that it has a left inverse.
let me remind you that if we know that A has a right inverse and a left inverse, then we know that those two have to be the same and that then A is invertible. But at this stage here, all what we really know is that A has a right inverse. We need then an auxiliary theorem, okay? So we need to complete the proof. We need to complete the proof. And auxiliary theorem that if A has a right inverse, then it must also have a left inverse, and so be invertible. Okay, so what we're going to have to do, it's a little bit, subtle, okay? So we're going to have to actually investigate this important point. It's a technical point, but it's actually quite important logically. And it turns out that to overcome that, we actually need to have a closer look at row reduction and how it connects with matrix multiplication. We'll do that in our next video, and then that will be able to allow us to complete this argument.